Thank you very much for the very kind introduction. And here we go. I start this talk with an introduction. Why do we teach geometry? It's not so that people can prove that the base angles of an isosceles triangle are equal. Really, there's little doubt about that. It's not so people can find the area of their living room. The people who lay down the rug can handle that. What I want to argue today is that geometry interacts with all aspects of human thought and life. And that understanding the way geometry interacts with all aspects of culture, is why it's important to teach it. So, we start with Euclid. I'm fond of saying that every mathematician has some sort of relationship with Euclid. This is not a photograph from life. Nobody knows what Euclid looked like. We know virtually nothing about him personally. He had a Greek name, but that doesn't even mean that he was a Greek. He worked in Alexandria in North Africa. Could have been an African. Who knows? But what makes Euclid so special? It's because whenever we use terms like truth and proof, what we're doing is channeling Euclid. For 2,000 years, Euclid's geometry seemed to prove truths about geometrical objects and thereby to achieve certainty. There's very little certainty in life. This man has it. Aristotle said that the truth and certainty of geometry comes from how it's put together, using logical deductions from explicit, self-evident assumptions and clear definitions. Euclid probably was looking over his shoulder at Aristotle and at Aristotle's criteria when he was writing the elements of geometry. And many important later thinkers believed that other subjects could come to share the certainty of geometry if only they followed the same method. Okay, these aren't going to be obscure people. Descartes, for instance, said, if we start with self-evident truths and then proceed by logically deducing more and more complex truths from these, why then, he says, there's nothing that we couldn't come to know. Okay? Spinoza wrote a book called Ethics Demonstrated in Geometrical Order, with explicitly labeled axioms and definitions, and including theorems like this one, quote, God, or substance consisting of infinite attributes, necessarily exists, end quote, whose proof he closes with QED. The influence of the Euclidean ideal on science is clear if you look at Newton's Principia. As you see, Newton called his famous 3 laws of motion axioms, and he deduced even his law of gravity in the form of 2 theorems. Newton summed this up rather well. It's the glory of geometry that from so few principles it can accomplish so much. One more example before the introduction is over. The Declaration of Independence of the United States is an argument whose author tried to inspire faith in its certainty by using the Euclidean form. Thomas Jefferson, who knew more of the mathematics of his time than any other American president, and some candidates for president, Jefferson began his argument thus: we hold these truths to be self-evident, that all right angles are equal. Well, no, that's not what he said, but that's what it sounds like. Another self-evident truth in the Declaration is that if any government fails to secure human rights, it's the right of the people to get rid of it and set up a new government. The Declaration then asserts that King George's government does not secure these rights. And then it says, quote, to prove this, let facts be submitted to a candid world. And that's the body of the Declaration of Independence, all those bad things that King George did. And then once the facts have proved this, we have an argument of this form. If P, then Q. I just proved P. Therefore, okay? And the actual declaration, the statement founding the United States independence, is stated explicitly as the conclusion of a logical argument beginning with a therefore. That is in the original. We therefore declare that these united colonies are, and of right ought to be, free and independent states. and so we are. So, in philosophy, theology, science, and politics, the idealized Euclidean model of reasoning has shaped conceptions of truth, proof, and certainty. Okay, that was the introduction. For the first half of the actual talk, we'll look at Euclid's elements, at the idea of Euclidean space, and some related ideas, and we'll look at their wide-ranging influence. We will see that Euclid's elements lives up to its press notices. But then we'll see, also, that there was a problem. And in the second half of the talk, we'll see that the problem and its resolution have produced a non-Euclidean world, and that break with the past has had a comparably great impact. Geometry is an actor in history. Okay, so here we go with part one. Here are Euclid's postulates, hopefully the minimal set of self-evident truths from which all the true results of geometry can be logically deduced. Postulates 1 through 4 are pretty straightforward, like, well, of course all right angles are equal. But look at number 5, Euclid's so-called parallel postulate, which doesn't mention parallels at all. I'm going to give you 4 seconds just to read it. Well, that one's complicated. I think we'd better draw a picture. Okay, so postulate 5 means this. If the two green lines, are they green? Can you see them? They don't have to be green, you understand. It's just that. If the two green lines are cut by a third line AB, such an angle A and angle B add up to less than 2 right angles, then the two green lines eventually meet on that side. That is Euclid's so-called parallel postulate. Now, I ask my students when I'm teaching this to vote on whether this postulate is self-evident. And they overwhelmingly agree that it's not, and somebody usually says, hey, you had to draw a picture before I even understood what it said. And that is the problem that I mentioned. The ancient Greeks agreed with my students. Well, okay, if the postulate is not self-evident, then maybe it doesn't have to be a postulate. Maybe we can prove it from the other postulates. So the Greeks tried to do that. Prove postulate 5 from postulates 1 through 4 and all the consequences of postulates 1 through 4. They didn't succeed. And lots of people kept on trying to do this. The mathematicians, the best mathematicians in the medieval Islamic and Jewish worlds tried to prove Euclid's 5th postulate from the others. More things that are not photographs from life. I learned when I published my book on Cauchy that if you don't want copyright difficulties, you should get portraits from stamps. So here are some really good mathematicians from medieval Islamic and Jewish culture who tried to prove the 5th postulate from postulates 1 through 4. And then on into Europe, on into the 19th century, another group of very famous mathematicians who tried and did not succeed in proving Euclid's 5th postulate. But when you're trying to prove something and it doesn't succeed, you learn things. When the Greeks were trying to prove the 5th postulate, one thing they proved right at the start was that Euclid's postulate is logically equivalent to the uniqueness of parallel lines. Given a line through an outside point in the same plane, there's only one line through that point parallel to the given line. Probably that's the postulate that you used in high school. It's named after John Playfair, an 18th century Scottish mathematician who wrote a geometry textbook called Playfair's Axiom, but it actually goes back at least to Proclus in the 5th century in the ancient world. But you can't name things after Greeks because nobody's heard of them except Euclid. Okay, now Euclid defined parallel lines as lines in the same plane that never meet. And from his first 4 postulates, given that definition, he proved that parallel lines can be constructed. He proved a number of properties of them, but he needs that problematic 5th postulate, which he uses very rarely. He needs that postulate for his proof of what is really the key theorem about parallels, which you all remember from high school. If 2 lines are parallel, the alternate interior angles and the corresponding angles are equal, like angle 3 equals angle 6, angle 2 equals angle 6 in my diagram. From that key theorem, which rests on postulate 5, From that key theorem, Euclid proves not only the uniqueness of parallels, but many other theorems involving parallel lines, like that they're everywhere equidistant, or that the sum of the angles of a triangle is 2 right angles, a theorem to which I will return. Okay, now Euclid doesn't talk about space, but later people do, and especially starting in the Renaissance, people talk a lot about space. What's space like? It's infinite. It's homogeneous, that is, every point is the same as every other point, and every direction is the same as every other direction. That's the space that Euclid's geometry happens in. And the role of philosophy in talking about Euclidean space is just enormous. The idea that space must be the same in all directions comes from what is called the principle of sufficient reason. I know this sounds trivial, but there it is. And the principle is at least as old as Archimedes, and I want to show you what he did with it. Here's an example of sufficient reason at work. How do you know that a lever with equal weights at equal distances from the fulcrum must balance? Because there's no reason for the lever to go down on either side. Therefore, it balances. And that's the principle of sufficient reason at work. Okay, now sufficient reason is also why space is infinite. Giordano Bruno in 1600 said, space has got to be infinite because there's no reason for it to stop at any particular point. All points are the same. Hence, space is infinite. That's a Renaissance idea, and that's where it comes from. Now, the greatest advocate of the principle of sufficient reason, you will recognize who this is Leibniz. Leibniz said it's the principle of sufficient reason, along with the laws of logic, that God used to make the universe. God made the universe optimal in the best possible way. Many scientific laws still use the language of optimization. The most obvious example, which Leibniz wrote on, is that light travels, when it is refracted, in the shortest possible time. For Leibniz, sufficient reason gives the simplest laws and the most efficient universe, and that's the kind God would make. Okay, now listen to this. If the principle of sufficient reason is true, then the universe should be transparent to reason. God made it rationally, so we human beings can figure it out. We don't even have to get our hands dirty doing experiments. Okay, now I know what you're thinking. You're thinking that's ridiculous. Nobody ever did that. Well, let me tell you the history of Newton's first law. You know Newton's first law. Okay, Newton's first law was discovered 50 years before Newton, independently by Descartes and Pierre Gassendi. And here's how they figured it out. The first law of motion says a body in motion with no forces acting on it continues in a straight line at a constant speed. Why? Well, the body continues in a straight line because every direction in space is the same. So why should it turn to the left or the right if it's already got a direction? No forces acting on it, right? And why does it go at a constant speed? Well, every point in space is the same. So why should it prefer being this point to that point? So why should it speed up? Or why should it slow down? So it continues at its constant speed. Exactly similar arguments make a body at rest with no forces acting on it stay right where it is. So, Newton's first law, brought to you courtesy of the principle of sufficient reason. And now we go back to parallels. The great mathematician, Joseph Louis Lagrange, decided that he could prove the uniqueness of parallels, thus effectively proving Euclid's postulate. How? By using the principle of sufficient reason. Remind you what he's going to prove? Well, wait a minute. Who says you can use the principle of sufficient reason in proofs in geometry? Lagrange says so. Okay? He says the principle of sufficient reason is just as obvious and true as are the laws of logic. Okay, now let's see what Lagrange did about this. It's in a manuscript that I found at the Institute of France, and I've published an article about it. and I think it's just absolutely fascinating. It's a proof by contradiction. Given that we have one parallel through point P, by the way, Euclid proves that without using postulate 5 that there are parallels. Given that we have one parallel through point P, suppose there were another one. It might look like this. Brief pause. It is very hard to draw convincing diagrams for things that are not true. This is why people like Descartes didn't like proof by contradiction. But anyway, here we go. All right, so here's your new parallel. But by the principle of sufficient reason, there's no reason that this new parallel line should be below the point P on the left and above the point P on the right. It could equally well be drawn the other way. So, principle of sufficient reason says there's another symmetric parallel line that goes the other way. Then Lagrange repeats this exact same argument for lines symmetric to his new parallels. So you get a third line on the other side of his new parallel, like this. And so on, with lots and lots more, and I will show you Lagrange's own picture from the manuscript of the final situation. Which, Lagrange says, is absurd. So, he concludes, there can only be one parallel, QED. All right, well, your reaction is what the reaction was of the other mathematicians at the Institute of France. He never published it. Maybe he came to see that when he used the principle of sufficient reason to produce his first set of new symmetric parallels, he was assuming that the original two parallel lines were everywhere equidistant. That's what makes the principle of sufficient reason applicable here, and therefore assuming the very Euclidean nature of space that he was trying to prove. But the fact that a great mathematician like Lagrange got up in public and linked space being Euclidean with Leibniz's principle of sufficient reason demonstrates how closely linked sufficient reason was with the necessity that space must be Euclidean. Oh yeah, and another thing, space has got to be real. Newton insisted upon this. Why? So he could distinguish real accelerations, like when your car is moving forward with respect to the garage wall. That's an acceleration with respect to space, as opposed to apparent accelerations when the garage wall is accelerating towards you. All right, then you don't get pushed back in your seat until, of course, it hits you. You can't have that. All right, because he wanted to argue that gravity was a real force, and that when the planet does not go in a straight line, but deviates from it to ellipse, is that the verb? To move elliptically around the sun, that's a real acceleration, therefore a real force, therefore gravity is real. Furthermore, that real space for Newton's physics has got to be Euclidean. Why? Well, back to a piece of the picture from Newton's Principia I showed you before. So we can do parallelograms of forces. There's all the properties of parallelograms that Newton uses in the theory of parallelograms of force requires Euclid's theory of parallels, and therefore postulate 5. Now Leibniz, you'd think he'd agree, right? Principle of sufficient reason and all that. But Leibniz disagreed with Newton about space. All that it is the relations between bodies. Well, that's an interesting argument. But Newton's view prevailed. Why? Well, here's another really important person coming down on Newton's side. Euler. Euler says this, look, the straight line constant speed motion of a single body with no forces acting on it, according to Newton's first law, that can't possibly depend on where other physical bodies just happen to be at some particular time. It's got to be a straight line always. It's got to be a straight line, therefore, with respect to something permanent, and that is space. So space has got to be real as well as Euclidean. Last mathematical question here. So, why did mathematicians of the 18th century care so much about proving the parallel postulate? Well, the reason is that it was so important. Not only geometry, but all of science rested on it. You really don't want all that resting on an assumption if you could possibly prove it. And now, switch gears to philosophy. A super influential philosopher, Immanuel Kant, agreed with Newton that space exists and that we order our perceptions in it, but Kant said space exists in our minds. And we each have the same unique space in our minds. And it turns out that, for Kant, this space has to be Euclidean. And I want to explain that, because he never says space has to be Euclidean. But it's true all the same, whatever he said. Let me show you. Kant uses geometry to demonstrate that we can come to know non-trivial truths about non-material things. I'm going to repeat that. Non-trivial truths about non-material things. Those of you who studied philosophy, synthetic a priori judgments are possible. Those of you who haven't, non-trivial truths about non-material things. Kant uses as an example Euclid's proof that the sum of the angles of a triangle is 2 right angles. Remind you how Euclid's proof goes. You start with a triangle. All right, now to do the proof, you begin by extending the base to D and then constructing a line through the corner parallel to the opposite side. CE is parallel to AB. And then you prove the equality of various angles in the triangle to the angles around C. And the angles around C, of course, add up to 2 right angles. The equal angles are specified in this slide, but it isn't the details of the proof that matter. Kant's key point is this: the proof can't work unless and until you make those constructions. Okay? So, where'd you make those constructions? Well, not on paper. Geometry isn't about triangles on paper. No, you made them in space, says Kant. And that space is in your mind. Now, Euclid's proof needs the result that if 2 lines are parallel, the alternate interior and corresponding angles are equal. As I said before, Euclid's proof of that theorem explicitly requires the 5th postulate. So this theorem about the sum of the angles of a triangle requires the space in our minds to be Euclidean. Now, Kant doesn't say this because he's writing in 1781 and nobody's ever suggested that there's non-Euclidean space. But what Kant does say is that there's only one space. The space in our mind is unique. So for Kant too, no alternative to Euclid seems conceivable. Okay, one more philosopher witness to the Euclidean space as truth, someone whose philosophy is a lot easier to read, Voltaire. Voltaire shares a widespread view in the 18th century that universal agreement is a marker for truth. He says, in religion you do not have universal agreement, he says. He says, though, listen guys, quote, there are no sects in geometry. One doesn't say, I'm a Euclidean. I'm an Archimedean. Demonstrate the truth, says Voltaire, and the whole world will be of your opinion. Mathematics exemplifies this, and Voltaire wants ethics to exemplify it too. Voltaire wrote, quote, there is but one morality, as there is but one geometry. And one of my students shot back, wrong on both points, Mr. Voltaire. But you see, that was the voice of the 21st century. In the 18th century, people agreed with Voltaire. Okay, the art and architecture of the early modern period also reflects the Euclidean nature of space. Art and architecture reinforced the Euclidean intuition of space in the minds of everybody who looked at the paintings and who lived and worked in the buildings and public squares from the Renaissance well into the 19th century. Perspective in art, based on Euclid's geometry, helped make people literally see space as Euclidean. And let me literally illustrate. This is the first important perspective painting of the Renaissance, the Trinity by Masaccio. Now, we are used to 2-dimensional pictures that look 3-dimensional because we've got photography and television and iPhones and stuff, screens like this. In the Renaissance, they didn't have those things, and so paintings like these, particularly exciting, incredibly exciting, really. Look at the quotation from Vasari. I mean, it's commonplace to us that this looks 3-dimensional, but it wasn't to them. Those of you who are not into art history, I'm going to show you a couple of medieval works of art so you can appreciate the difference between medieval and Renaissance art. Right, this is a very famous picture of Harold, who lost to William the Conqueror. That's Halley's Comet up there. They didn't know that yet. Up in the air. But look, the people in the castle are the same size. There's no three-dimensionality here. This is crossing the Red Sea. Notice the way the Red Sea runs from the top of the picture to the bottom, and notice that it's just the same size as the people. Now, I mean, this is lovely art, but it's not convincingly three-dimensional. In the Renaissance, though, we are in a different kind of space. The geometry used in creating Renaissance art is literally Euclidean. It comes partly from Euclid's elements of geometry and partly from Euclid's optics. Here's one of the things that Euclid proved in his optics. This is not the picture from Euclid's optics, but it illustrates this it illustrates the theorem really, really well. Among the things that Euclid proved in the elements that are relevant to art is this theorem. A straight line parallel to the base of the triangle cuts the other two sides proportionally. And the proof of this theorem needs Euclid's fifth postulate. Okay, let me show you how this geometry lets us see three-dimensional reality on a flat canvas. This is the Alberti construction. It's a two-dimensional drawing of a square floor that is itself divided into squares like a checkerboard. The square in question is perpendicular to the plane of the screen. The parallel sides of the squares that are perpendicular to the screen, the little squares, appear in this picture to meet when you extend them at a point, which is called the principal vanishing point. This photograph does the Alberti construction for two parallel railroad tracks perpendicular to the plane of the screen. Fortunately, there's no train in this picture to threaten you. Okay, now the checkerboard construction, if you look at it, is just full of similar triangles. And this checkerboard construction was used in paintings by many painters. It's not the first thing that you see when you look at a great Renaissance painting is the checkerboard, but let me show you two examples from very important painters who were also accomplished at mathematics. This is a very dramatic scene from the life of Jesus. I call your attention not to the man with the whip who is there at the principal vanishing point, but to the checkerboard, which makes the perspective more convincing. Here's an even more famous painting. I don't think that the early Christians had the Last Supper in a building with a checkerboard on the roof, but Leonardo wants you to get the perspective. Principal vanishing point here is on the face of Jesus. Now, moving north from Italy into Germany, here's another mathematician artist, Albrecht Dürer, showing you how to construct point by point the image of something on a screen. Did artists need to master all this mathematical theory in order to draw in three dimensions? Because they didn't all know as much mathematics as Piero and Leonardo. Answer is no. Erhard Schön is a student of Dürer, and here's what he said. Just look at my drawing, and then you'll know what to do. Here's another German example by Count Johann. I like this picture because it literally embodies Euclid's theorem about the proportional sides of similar triangles. I'm going to show you one more Renaissance art example while I sum this all up. Those of you who were at Professor Corrali's talk this morning have seen this painting already. This is Raphael's The School of Athens. The guy with the little chalkboard on the lower right is sometimes thought to be Pythagoras and sometimes Euclid, so he's paying homage to his geometrical master. The objects in this painting look the way an objective observer on the scene would actually see them, in a rational order created by Euclid's geometry. The art helps teach us to see our world as Euclidean. Architecture also teaches us to see our world as Euclidean. Now, whenever I talk about this, I'm always in a room like this one. full of parallel lines. Look at that wall. Look at that wall. Look at the screen. Look at all the rectangles in the back. Look at the ceiling. This room is full of examples of parallel lines intersecting another line and making equal angles when they do so. That is the theorem that needs postulate 5 to prove, and this is the kind of room you would design if what you wanted to do was brainwash the people in it to believe that space is Euclidean. Okay, so here's the 18th century world, the world of sufficient reason. Symmetric, balanced, based on self-evident and necessary truths, embedded in Euclidean space. And we can figure it all out rationally by ourselves because we are reasonable also. Euclid's geometry is the universally agreed upon model of perfect intellectual authority. And I'm going to repeat that, the 18th century view. Euclid's geometry is the universally agreed upon model of perfect intellectual authority. That's the end of part 1 of the talk, and now part 2 is going to blow it all out of the water. It's really amazing that in the early 19th century, Gauss, Bolyai, and Lobachevsky, the 3 independent inventors of the first non-Euclidean geometries, were able, in spite of all this Euclidean brainwashing, to imagine that space could be other than Euclidean. What they did was to realize that the absurd consequences of denying Euclid's postulate, consequences like that, hey, parallels aren't everywhere equidistant, parallel lines through an outside point aren't unique, that those consequences were not absurd at all, but instead are truths, but truths in some alternate, counterintuitive reality. Alternate, counterintuitive reality. Well, the walls of this room are not the correct place to look for this alternate reality. So, this is a hyperbolic paraboloid. It's a modern, non-Euclidean surface. I stole the plaster model from the Pomona College mathematics department when Pomona College goes back to the 1890s, and they bought models like this in order to teach about the non-Euclidean surfaces, having not had Mathematica installed in the 1890s. Okay, what you see illustrated here is a surface that obeys Euclid's first 4 postulates but disobeys the 5th. You'll notice that the red and yellow shortest paths never meet their parallel, the blue one. They never meet the blue one, so they're parallel by Euclid's definition to the blue one, but notice they intersect with each other up there at the top. And notice that, say, the blue and yellow parallel lines are clearly not everywhere equidistant. So this is an example of a non-Euclidean surface. The idea of non-Euclidean geometry was so revolutionary that Gauss, one of the discoverers, never got up the nerve to publish his work on this subject. Non-Euclidean geometry required a paradigm change, realizing that the logical implications of denying Euclid's postulate, like the non-uniqueness of parallels, that they weren't intellectual absurdities as Lagrange had thought, but part of an alternate reality. The Lobachevskian version of non-Euclidean geometry with space of negative curvature was of course not the only one. There are lots more, including spaces of positive curvature, a whole class of things that don't obey Euclid's postulate, as was explained to mathematicians, notably by Bernhard Riemann. Well, okay, for mathematics, but what about philosophy? Like, what about Kant's philosophy, right? That space is in the mind, and that the properties of space are the same for all human beings? And after all, we order our perceptions in space, don't we? Of course we do. You're sitting there right there, whether you realize you're doing it or not, ordering your perceptions in space. I am here, and that's over there, and the ceiling is above us, and the floor is below us, and okay, those ideas above and below and so on, okay, those are spatial ideas. You're ordering your perceptions in space. Euclidean space. We can't possibly order our perceptions in a non-Euclidean space. Can we? Well, if Kant were here, he would say, no, you're right, Professor Grabiner. No, you can't. But yes, we can. So says Hermann von Helmholtz. Of course, in order to order our perceptions in a three-dimensional non-Euclidean space, we've got to divest ourselves of 2,000 years of Euclidean experience, also the room we're in. But if we can order our perceptions in a three-dimensional non-Euclidean space, then Kant is wrong. And if Kant is wrong, says Helmholtz, the postulates of geometry are not dictated by the nature of the human intellect. For Helmholtz, whether space is Euclidean or not is a question for experience. Okay, so let's see if through new experiences you can learn to order your perceptions in a non-Euclidean three-dimensional space. Here's how. Look at the reflections in a convex mirror. Now you probably have one of these on your car, right? There's a little warning on it, right? Here's what the warning means. Warning! The space you see in this mirror is not Euclidean. All right, so here's a three-dimensional non-Euclidean space. You see the parallel lines at the top and the bottom of the bookcase not being everywhere equidistant? So there you are. Can we learn to order our perceptions in such a space? Well, if you've made it safely so far looking into your car's convex mirror, then yes, you can. Okay, but you might not be convinced by this argument. You might say, look, all right, yeah, but I mean, that's a mirror, okay? It's just an illusion, the world in the mirror. Only our own world the Euclidean world is real. And Helmholtz says, are you so sure? Suppose you're having a dialogue with the guy, this is Helmholtz's argument, not mine. Suppose you're having a dialogue with the guy in the mirror. You say to the guy in the mirror, my world is real, yours is distorted. He says, really? How can you tell? You say, well, in your world, when you get closer to the mirror, you get bigger. And when you go farther away from the mirror, you get smaller. Now that violates the obvious self-evident Euclidean fact that when you move something around through space, it stays the same size and shape. The guy in the mirror says, really? Gosh, let me try that. So he takes a yardstick. He comes up near the interface between his world and yours, and ours, and he measures himself. I'm 6 feet tall, he says. And then he goes off to the back of the room, far away from the mirror, and he measures himself again. And he says, no, you're wrong. I'm still 6 feet tall. And you say, no, but your yardstick changed its size too. And he says, that's the most preposterous explanation I've ever heard. Okay. Helmholtz says, there's no geometrical experiment that you can do that will decide the question of which one of these worlds is the real one. Does that sound like relativity to you? It's no accident, because there is a line of historical influence in German philosophy, from Helmholtz to Ernst Mach, and then on to Einstein. Okay. Bothered some people. The British mathematician and philosopher W.K. Clifford argued that the new geometry was like the Copernican revolution. Briefly, the Earth used to be in the center of the universe and everything went around it. Now, everything in the solar system goes around the sun, and there are lots of other suns out there, and that's the Copernican revolution, okay? Clifford said, it used to be that the aim of every scientific student of every subject was to bring his knowledge of that subject into a form as perfect as that which geometry had attained. But no more. Before Copernicus, said Clifford, people thought they knew all about the whole universe. Now we know only one small piece of it. Likewise, before non-Euclidean geometry, the laws of space and motion implied an infinite space whose properties were always the same. No more, said Clifford. Sure, space appears flat and continuous, but only so far as we can explore. and no farther. Okay, that's a big change, and he is one of the first people to really clearly explain philosophically what was at stake. You think that's revolutionary? It gets more revolutionary. We look at Poincaré. Poincaré also saw the new geometries as revolutionary, but he disagreed both with Kant and with Helmholtz. Okay, here's why Helmholtz is wrong. If, as Helmholtz says, geometry comes from experience, then geometry wouldn't be an exact science. It would just be physics. Still, Poincaré is way on the other side of the non-Euclidean revolution in geometry, so he knows perfectly well that we have more than one kind of space in our minds. So, the postulates of geometry are not synthetic a priori intuitions, as Kant said. They're not experimental facts, as Helmholtz said. And they aren't necessary self-evident truths, as Voltaire and Lagrange said. Geometrical axioms, says Poincaré, are conventions. Conventions. Well, okay, so how should we decide which set of axioms to use? Those of Euclid, Lobachevsky, or Riemann? Poincaré says this in response. Our choice among all possible conventions may be guided by experience, but as long as we avoid contradictions, our choice remains free. So what are we to think of the question, is Euclidean geometry true? The question has no meaning. We might as well ask if the metric system is true and the old weights and measures false. One geometry cannot be more true than another. It can only be more convenient. This is revolutionary too. Mathematics, according to Poincaré and others at the end of the 19th century, no longer exactly fits reality. A reality that must obey principles like sufficient reason. We now just choose the mathematical model that does best what we want it to do. Now, in the 20th century, it turned out that non-Euclidean geometries of the Riemannian type, that's positively curved space, were in fact more convenient because Riemann's non-Euclidean geometry is exactly what Einstein needed to do general relativity. According to Einstein's theory of gravity, the paths of planets moving under gravity are shortest distances in a non-Euclidean space-time. Light no longer travels in Euclidean straight lines, but shortest distances in a non-Euclidean space-time manifold. Is real space really Riemannian? Poincaré would say, that's what works. And non-Euclidean geometry was essential to general relativity. Einstein's general theory of relativity overthrew the old Newtonian Euclidean certainty to a new relativistic conception of reality and caused a public sensation. I have here a newspaper article, not a scientific journal, to indicate the nature of the public sensation. And it also revolutionized how people thought about space. Regular people, not physicists and mathematicians and unusual people like that. Even before non-Euclidean geometry, philosophers, notably Bishop Berkeley, brief pause. Berkeley is spelled Berkeley, the town is named after him. He's a very interesting 18th century philosopher. And one of the things that he said is that we don't see distance. What we see are visual angles. And we infer the geometry of what's out there from the angles that we actually see. Here's this is not his example, this is mine, but it's a really easy example of the kind of thing that philosophers like Berkeley are talking about. Look at the corner of a room where the ceiling and two walls meet. And if I asked you what's going on, you would say, there are three 90-degree angles coming together. But look, that's not three 90-degree angles coming together. That's 320-degree angles coming together. Our visual space is not the same as the space we claim to see. And the invention of non-Euclidean geometry really made psychologists to think a lot about things like this. Like Helmholtz. Helmholtz, besides being a great physicist, co-discoverer of the conservation of energy, and philosopher who talked about geometry, did a lot of work on the psychology of perception. So he did an experiment. He put people in a dark room with a table in front of them, long table, and with sticks so that they could manipulate objects. And on the table put a lot of little points of light, kind of like those little candle things that you have, you know? And turned off all the lights and told people to use the sticks to make the little lights in front of them into two parallel lines moving away from the observer. Okay? You think you could do that? Well, what turned out the people did was that the lines weren't parallel at all. They turned out to curve away from the observer. And so Helmholtz concluded that visual space was Lobachevskian. But now, the prevailing view now seems to be that the space of visual perception isn't represented by any consistent geometry. Okay, now this is all European material. What happens in other cultures? Well, in fact, the cultural linguist Stephen Levinson has shown that people in different cultures have other ways of ordering their perceptions than in an external Euclidean space. Some cultures do use the idea of a fixed coordinate system in space, using 4 cardinal directions, as if I were to say, my car is parked to the south of this building. That's like Newton's absolute spatial framework. But other cultures order their perceptions in space more in line with Leibniz's idea about the relation between bodies. Some do it from the individual's point of view, as if I were to walk outside and say, the car is to the right of the building. That's my right. Or you could get the individual out of it also, as if I were to say, my car is at the front of the building. There it's just the intrinsic properties of the objects that give me the spatial ordering. There's no framework, and I'm not in that either. In our own culture, GPS navigational systems are changing people's supposedly innate intuitions of space from the Newtonian to the Leibnizian. And this actually happened to me. While I was going to my son's house in Maryland, I asked the taxi driver, who said he just had the GPS for a few weeks, I asked him whether it had changed the way he thought about space. And he got really excited about the question. He said, yeah! He said, you know, I used to have the whole geography of greater Baltimore in my head. I don't anymore. Like to take you somewhere, he said. I'll turn left out of the airport, I'll take the expressway to such and such exit, then I'll turn right. Then after I've left you off, I'll just reverse that. I'll turn left, I'll get on the expressway, and I'll turn right into the airport. I'll get back, I'll get you where you're going, and I'll get back. But I won't know where I've been. And I thought that was just so interesting. I pulled out a piece of paper and I wrote it down. Okay, now let's get back to the cultural paradigm shift from Euclidean geometry to non-Euclidean geometry by means of a classroom anecdote. When I teach this, I pass a convex mirror around. And one of the students looked at the mirror, convex mirror, looked at himself in the convex mirror, and he said, "This is distorted." And somebody else said, "No, it's not. You're a Euclidean chauvinist." Okay, and that exchange makes us aware that there's something cultural going on, given the phrase chauvinist. And so I want to look a little bit about what some modern influential theorists of culture have had to say about this paradigm shift. The most revolutionary implication of the paradigm shift denies that we can have absolute knowledge about anything. One especially influential thinker on this topic was the Spaniard José Ortega y Gasset. Using both non-Euclidean geometry and relativity, Ortega drew revolutionary cultural and political conclusions in order to refute what he called the dogmatisms of absolutism, provincialism, utopianism, and rationalism. All these 18th century guys are now turning over in their graves, okay? Ortega wrote an essay called The Historical Significance of the Theory of Einstein. He first used the new geometries to argue that provincialism assuming that our own experience or values are universal, is wrong. That mirrors what Clifford said, the quotation I gave you before. Euclidean geometry, Ortega says, was provincial. It was an unwarranted extrapolation of what was locally observed to the whole universe. Instead, says Ortega, reality organizes itself to be visible from all viewpoints. He said, Einstein's theory of relativity, which requires new geometries of space-time, promotes the harmonious multiplicity of all possible points of view. I'm going to repeat that phrase, the harmonious multiplicity of all possible points of view. Keep that in your mind for a few minutes. And not just for mathematics and physics, said Ortega, also for politics and culture. There is a Chinese perspective, Ortega says, that is fully as justified as the Western. All absolutisms are wrong, says Ortega, whether in geometry, physics, or philosophy. Reality, says Ortega, is relative. The last two of Ortega's dogmatisms, utopianism and rationalism, are linked, and again they're both wrong. Since the Greeks, Ortega says, reason has tried to build an idealized world and say, this is true, this is how it is. Before relativity theory, Hendrik Lorentz said, matter must get smaller as it goes faster. That is, said Ortega, for Lorentz, matter yields so that the old laws of physics can continue to hold. But Einstein said instead, no, space yields. Geometry must yield. Space itself must curve. And here's what Ortega does politically from that. According to Ortega, Lorentz might say, nations may perish, but we will keep our principles. Einstein, according to Ortega, would reply, no, we must look for such principles as will preserve nations, because that is what principles are for. There are some other examples of influential radical thinking facilitated by new views of geometry. Bachelard was a surrealist theorist. He wrote an essay attacking both reason and logic. Bachelard wanted to restore reason to its true function. Reason is not designed to shore up the agreed upon order, he said. Instead, as the new geometries show, reason is a turbulent aggression. Russian thinker P.D. Ouspensky not only attacked the limitations of three-dimensional space, which he identified with Euclidean geometry, but attacked Aristotle, in fact, all of deductive logic. See, Aristotle's logic has the law of the excluded middle. Everything is either A or not A, right? No, not right. Ouspensky wrote, A is both A and not A. Furthermore, everything is both A and not A. Well, so much for the Euclidean ideal of deductive reasoning. Let me say something about the title of his book, The Third Organon. Aristotle's logic was called the organon, instrument of finding truths. In the 17th century, Francis Bacon, who championed inductive reasoning over deductive reasoning, wrote a new organon, the Novum Organum. Okay, so this is number 3 in the list. At least he didn't throw out the small hole numbers. Another very influential French cultural theorist, Jean Baudrillard, used non-Euclidean geometry to annihilate the science-based idea of progress, saying the straight line scientific progress and democracy thing only pertains to the linear space of the Enlightenment. In our non-Euclidean space at the end of the 20th century, a malevolent curvature invincibly reroutes all trajectories. That's certainly beautiful prose. Let's go back to architecture. I want you to look at some of the work of Zaha Hadid, the first woman to win the Pritzker Architecture Prize. As an undergraduate, she majored in mathematics. We aren't in the Renaissance ideal city anymore. Here's what she says about the world of the 21st century. The most important thing is motion, the flux of things, a non-Euclidean geometry in which nothing repeats itself, a new order of space. The new geometries have inspired many different types of artistic freedom. First, I want to give you a couple of examples from Cubist art of what Ortega, I'm going to quote you this phrase back again, of what Ortega called, quote, reality organizing itself to be seen from all points of view. This is not a terribly well-known painting. I saw it in the Philadelphia Art Museum, and I thought that was, that's the one Rocky runs up the steps. Philadelphia. It's a really fine art museum for many reasons. Anyway, I want you to look at the teacup in this picture, and you see the reality organized so you can see it from a variety of points of view. Her face too, but it's really striking with the teacup because you can see geometrically what's going on. Here is a more famous painting. This is one of Picasso's patrons. I hope he liked it. Notice the planes and angles from the multiple points of view, and notice something else. This man is not placed in a visually graspable three-dimensional space at all. Space yields. This is no accident. It's directly related to non-Euclidean geometry. Picasso listened to a series of lectures by the artist and philosopher Maurice Pincet, P-R-I-N-C-E-T, on non-Euclidean geometry in the fourth dimension. Oh yeah, and remember Poincaré? Pincet's lectures were largely based on the writings of Poincaré. Now, here's a different kind of geometrical influence on art. As I said, around the end of the 19th century, mathematicians began using physical models to teach and study the geometry of non-Euclidean surfaces, like the plaster model that I borrowed from Pomona College. There's a great collection of such models in Paris. Where in Paris? At the Poincaré Institute. Isn't that cool? I want to show you a few examples of those models and their influence on art. Man Ray is a very, very interesting artist. He has this series of Shakespearean expressions. So there you got three of the models from the Poincaré Institute whose mathematical details are at the bottom of the screen. He's put them together in this thing that he calls Twelfth Night. Twelfth Night is a play by Shakespeare in which there is a lot of boundary crossing. It's a wonderful play. And this is a geometric representation of what he thought that play was about. It's just remarkable. More conventional play by Shakespeare is King Lear. And on the left is the model. In the middle is the photograph of the model from the Poincaré Institute. And on the right is the work of art called King Lear that Man Ray made about it. And he's played with the geometry in the way that's described up there. And if you want to think of that as King Lear and his three daughters, you can. What Man Ray said after the first time he was at the Poincaré Institute. Here's another kind of example from the Poincaré Institute. And following, I'll show you the work of two artists who were inspired by string models like that one. One's called Linear Construction, number 4. And the other is a model for a sculpture called The World. Well, I say we live in a world of interesting geometry. That one makes that point. One of the surrealist artists, Max Ernst, is the guy who told Man Ray to go look at the shapes in the Poincaré Institute. Here is a painting by Max Ernst, and on the right, the geometric shapes that were suggestive to him. I like the concept of a non-Euclidean fly. You can, if you get angry at a fly buzzing around your head during your mathematics class, you can call it a non-Euclidean fly and swat it and show your students this if you want. Okay, 20th century artists attack logic and attack Euclidean geometry, and they say that the artist's imagination should transcend all limitations, just like what Einstein did. For instance, you say that parallel lines can't meet? Well, they can if they want to. This is a surrealist painting by Yves Tanguy, and there you see all the parallel lines meeting in this surreal landscape. So, artists are influenced by the new geometry. They cite its authority and its prestige on their behalf. They use it as part of their creation of self-consciously modern art, and they help us see a different world. Coming now to my last pair of slides, here's the first. I found this searching using Google Image for hyperbolic paraboloid. And I like this picture particularly because it shows us how much non-Euclidean geometrical objects had become part of the general culture already more than half a century ago. I keep trying to come up with a clever remark about we're not in Kansas anymore, but we are, so, well, that's the best I can do. And here's another work of architecture that became internationally famous just a very few years ago. That's the Olympic Velodrome in London, and they called it the Pringle. Well, if you want some non-Euclidean surfaces, you can go and buy a tin of Pringles because that's what they are, and that's what happens when you take slices of potato and cook them in oil. They become hyperbolic paraboloids. Isn't that nice? Okay, I want to now give you a conclusion. Twice in history, first in Euclid's world and then in the non-Euclidean world, ideas about geometry have shaped art and architecture, have shaped physics and philosophy, and have shaped the way people see and think about the world. Euclidean geometry said, reason can figure out the whole universe, and it's symmetric, and it's stable, and it's uniform, and there's a reason for everything, and everybody who studies it, once they understand, will come to agree. Well, I hope I don't have to tell you that that is not the world we live in now. The creation of non-Euclidean geometry had a lot to do with the way all of us think about the world that we do live in. So last sentence, geometry is the backbone of civilization. We need to let our students in on this. Thank you.
So, do you have any questions for Dr. Grabiner? I guess not. Oh, yes.
So what are you most excited about to look at in the next couple of years? We're going to have all this time to look at when we retire.
Who, me?
Yeah.
Well, let's say I have an infinite universe.
Anything else? Right. Once again, if anybody's interested, Dr. Grabiner also has a course available from the teaching company called the Mathematics, Philosophy, and the Real World. So once again, if you guys give another warm round of applause for Dr.